Okay. So our next section we're going to look at for hydraulics. I know we've been away for a bit, but we'll continue here. Has to deal with valves and trying to make it so it's easier to see. So various valves that are in the hydraulic systems and how we're going to use them. I don't want you guys falling asleep. The lights in this room work different than every other room. No. Oh boy. There's supposed to be an in-between. There we go. That's kind of in between. But we're going to look at various types of valves, starting with, we're going to look at flow control valves, so turning it on and off, rates of flow, direction of flow, and moving it from one component to another, or like selecting. Pressure control, so we want to be able to we set our pressure in our system, but sometimes you have areas in the system where you don't want the full system pressure. You want to be able to regulate the pressure in areas. Various valves that are used to allow flow in only one direction or allow flow in one direction and restrict it in another. Selection valves, sequencing and priority. What goes first, what goes second, what goes third. Flow equalization, hydraulic fuses, and pressure control and regulators I was just talking about. So first thing we're going to look at are check valves because they're the simplest type, and a lot of this should hopefully be kind of review from basic systems because these same types of valves are used in both transport aircraft as well as general aviation aircraft. But check valves, very simple, allow flow in one direction and not the other. And so they're the two basic types we see, actually three basic types we see, but the two we mainly see in larger aircraft are going to be a ball type check valve. So the flow on all of these is from left to right. Fluid flow is able to push the ball, push against the spring, move it off the seat right here, and allow fluid flow left to right. Cone type check valves do the same thing, except here it's going to go through these passages on each side of the cone. And then you have flapper type check valves. These aren't used as much in our high pressure systems. The ball and the cone ones are going to be able to handle higher pressures, especially reverse pressures. Flapper type check valves tend to be used more in lower pressure or pneumatic type systems. A lot of these, there's commonality between pneumatic systems, hydraulic systems. They're both a fluid flow at the end of the day. So those flapper valves tend to be more pneumatic systems. We also have things called snubber valves, and these are different than the wheel snubbers. But at the end of the day, a snubber is something that slows things down. Okay, so some of you have looked at the gear on the 727 where there are snubbers for the nose wheels to slow them down when the gear retracts. In this case, snubbers are going to slow down or restrict the flow of fluid in one direction. So a snubber or orifice check valve, it allows free flow of fluid in one direction while it restricts it in the other. So an example here is this orifice check valve. This is a ball style. You can have, pressure is going to push off the seat, so it's going to be relatively free flowing from left to right, or it's going to be able to open a large passage. But from right to left, it's going to be able to, a little bit of fluid is going to be able to travel through that kind of bypass or orifice passage right there. Okay. Different class. That's okay. You can also have orifice check valves of the cone type here. And the way they do that is essentially there's a hole in the center of the cone at the end. And so when you have flow from left to right, it pushes the cone off the seat. This is a spring right here, all these little circls behind it. Can push this cone off the seat to get a higher flow rate from left to right. When fluid flows back, there would be a small and a snubber type check valve that uses a cone. There'd be a small hole in the middle restricting fluid flow from right to left. So does anyone who I didn't explain these to yesterday, because I know there was one person I told, know where we would often see these? Where would you want fluid flow free in one direction but often restricted in the other? And I can't remember who I talked to yesterday about why these exist. Who was that? I don't remember. It was you? Okay. Any ideas why? Um, maybe Jeremy talked about it with you? Fuel? Okay. So it tends to deal with actuators. So the one where these are most common, and it's a landing gear thing, that's why it came up yesterday with the group that was doing the landing gear lab, is when you retract your landing gear, you want all that pressure to pull the gear up. Right? It takes a lot of energy to get that gear to pull up because you're fighting against gravity. When you go to extend your landing gear, you don't want the landing gear to fall, right? You've got all that energy, the gear wants to fall. So if you, but so you put it where, like this ball type check valve here, when we're retracting the gear, fluid flow would be from left to right. So it's going to be able to push the gear up fairly quickly, and the fluid flow is more easy, less restricted. But then when we release the up locks and we want that gear to go back down, we don't want it just to fall and slam. So that orifice is going to restrict or allow the fluid to flow less quickly out of the actuator in order to kind of dampen the movement of the gear opening. Okay, so free flowing up, dampened opening of the gear. Okay. The next type we have are selector valves, and these we need to direct fluid in different directions. So a lot of our other valves we'll look at are going to be valves that are directing, selecting fluid flow, but then are built on various ways for special applications. But in the general sense, there are two types: rotary valves, spool valves. And rotary, you've probably seen tend to be more common in small aircraft systems, but they do occasionally pop up in large aircraft. We'll see mostly spool valves in larger aircraft. But these can be, we classify them by the type: are they rotary or spool? And we'll look at what those look like in a second. The other way we have to classify them is how are they operated. So just to go back, check valves, there is no operation. They're operated by the fluid flow itself. Right? Fluid from left to right is going to push the check valves open. Fluid from right to left is going to, there's a spring that'll push it shut and it won't be able to go. But for selector valves, we have to operate them. The simplest form is a manual. You reach down with your hand and you move the valve. Have you done a manual valve somewhere on an aircraft that we've been working on in lab? Anyone operated a manual hydraulic valve? What's that? The tail stairs. The valve for the air stairs on the 727 is a manual valve, okay? Now, that's probably not very common. You won't see very many of those. Anything else we've done with hydraulics, it's been operated some other way, right? So they can be spring operated, they can be solenoid, they can be mechanically operated. Flight controls are a mechanically operated valve. Or you can have pressure, which are called pilot valves, where you use a little bit of system pressure to actually move it. Okay, so technically, I guess you could call a check valve a type of pilot valve, right? We use some system pressure to move it. But this is more of if we need to, rather than, if we have like a lever to move a valve, rather than, the pressure pushing on the valve and physically opening it, a pressure pilot valve is that there would be like a little actuator that operates the lever, and we use hydraulic fluid to move that lever back and forth. So looking at them, here's our rotary selector valves. So here you can see we have our pressure manifold, we have our return manifold, and rotating this in different directions is going to move our cylinder, our actuating cylinder, one direction or the other. So right now, pressure is going to be routed to the right-hand side, okay? In the drawing, that's going to, they show, extending the piston is to the right. This is going to retract the piston to the left. When we retract it, when we move this actuator to the left, we have to have somewhere for the fluid on this side to go, on the left. And so you can see that same valve is also porting fluid up to our return side. If we rotate this valve to the other direction, what's shown with the dashed lines, that would route pressure to the left of the cylinder. But we have to allow that fluid on the right side of the cylinder to return, so it'd be able to do that. And then because this is a closed center system, when we're not moving the valve one way or the other, it's going to have a neutral position down here where those passages are not aligned with any of the pressure return lines. And that's going to, one, it's going to separate the pressure and the return side, right? That's that closed center system. Pressure manifold, return manifold are always separated. You know. But it's also going to hydraulically lock the actuator. Right? You can imagine if these ports are in the position shown here in the neutral position, it's going to close off the line going to the right side of the actuator. It's going to close off the line going to the left side of the actuator, and this piston will not be able to move, right? Hydraulic fluid is non-compressible, so we can hydraulically lock it. Okay. The other type of selector valve we have uses a spool, and it gets the term because in its simplest form, if we just look at the part that does the actuation right here, what does that look like? Where does the term spool come from? What's it look like? Where have you seen that shape? A what? Like a thread, a spool of thread, or a spool of wire. A spool, you know, it's a spool that stores something that's tend to be long and skinny. Right? Thread, electrical wire, you know, that kind of thing. So they're spooled. Now they can be a single spool like what's shown in these diagrams. They can also be multiple spools stacked on top of each other if you want to have all kinds of different ports going on and off of that valve, where it can do a lot of different jobs at once. You'll see some of these where they'll have spools. They'll have, you know, these are, you know, this is the passage in the middle. They'll have 5 or 6 or 7 or 8 or 9 different passages on it that can kind of do all different things as that spool shifts left and right. So it can be a single spool or, you know, simple or multi-spool. You know, in our earlier diagram, we had to have a way for, you know, 2 things had to open and close simultaneously here, right, with our rotary valve. That's what's being shown here on the right side as well. So if we have a spool and they put a passage through the middle of it, now we can use that same spool valve to operate a cylinder in 2 different directions. Okay? So pressure is hooked up to the top left, returns on the top right. So in the instance shown on the left, pressure comes in, it can pass around the skinny area of the spool on the outside. And that is being routed, in this case, to the right side of the cylinder. So it's going to push the cylinder from right to left, the actuator from right to left. Now the space to the left of the actuator piston, that has to be able to go somewhere. So it goes up, and they have a passage through the center of the spool that goes over to the return side. Okay. To move the actuator the other direction, you can see with the spool pushed over, where it's been pushed kind of past. Now the pressure is able to go past the actuating rod for the spool down to the left side, and return goes here. That passage through the center of the spool isn't being used. There's a third scenario, the neutral position. Where is the neutral position? It's not shown here. What would happen to make this a neutral position? What would we do? What's that? Covers both the pressure return. You can see here that these 2 spool ends, the thick parts, are about basically the same distance apart as the pressure and return lines, or they're the same distance apart as the lines going out to the valve. So we can move it into a position where it covers pressure and return. When it covers pressure and return, it also is going to separate, you know, there's no way for either of the lines going out. It could cover either the pressure and the return, or it could cover both of the lines going out to the cylinder. Either way, it's going to isolate and lock off, hydraulically lock the cylinder, and it's going to isolate the pressure and the return side of the hydraulic system from each other. So I have a video that shows these in operation. Okay. So those are 2 kind of styles of valves, and what you'll see, again, most often in transport category are going to be spool type valves. Okay. What's shown here on the left, these are standard diagrams for hydraulic valves. You don't see them a ton in aviation, but they basically show, you know, what ports are, you know, where fluid flow goes, or what ports are being capped off that kind of thing. And so if you do industrial hydraulics, you'll see a lot of these diagrams right here. And then the little zigzag line at the end, these have springs. So in the case of like this upper valve, you push it in to, you know, you see the springs compress, that ports fluid to the red side. When you let go of it, it's going to push it back to this way, and that'll port the top and blue ports together under normal circumstances. So just kind of shows some different things happening there. But most of our valves are going to be this, or they're going to be a servo or a pilot valve like we saw in the video a second ago. So another type of valve that we have is called a sequencing valve. And so this kind of goes to the, looking at it from like a gear. Gear tends to be the simplest, some of the simpler hydraulic systems to explain. And so that's where you'll see a lot of these explanations revolving around gear. But sequencing valves are mechanically actuated, you can say mechanically actuated check valves. So where one component operates for the other. So what we have here is an example where the selector valve has been put into the gear down position, okay? And so the first thing that we need to do is open the gear doors if they're closed. So fluid pressure, you can see, goes directly to the door actuator first, and pushing it down allows it to open. And you can see fluid's going to be able to flow out the non-actuation side through a check valve and back to the return. Now, there's a second valve here where it's a check valve it's a sequencing check valve. You can see it's in the closed position. Once the gear door reaches its open position, it's going to push this plunger on the sequence valve. That's going to allow fluid to flow, and it's going to go to the gear down. Now, in this case, the actuator is retracting to bring the gear down. Okay, sometimes you have actuators that, you know, retract to go down and extend to go up. They can be the other way. Just depends on the aircraft. So here, that'll allow the gear to go down and return. You can see there's a free path on the return side here. So this is one component, the gear doors, their movement is going to operate the sequence valve in order to then tell the gear it's safe to operate. Right? Doors open. Once the doors are open, then fluid is ported to the gear. Okay? And we have a lot of these going on. If you run like the flaps and slats, oftentimes like the slats will go down a bit, and then the flaps have to go down, then maybe the slats go down some more, and the flaps, you get a lot of that sequencing. Nowadays, modern flight controls, a lot of that is done with a computer. But older aircraft often use these kind of sequencing valves in order to handle those sequences that you're not going to manually do. Like, you're not going to manually retract the flat or the slats 5 degrees, and then you got to retract the flaps a few degrees, and then you got to retract the slats some more, right? So it was done this way. Or like your gear, instead of having, okay, first I have to move the switch that opens the gear doors, and then I move the switch that drops the gear, we just have a gear handle, and then this part is taken care of for you in the background. Priority valves do a similar job, but a priority valve, instead of using a mechanical, so sequence valves are mechanical. The gear, in this case, the actuator pushes this little button. Priority valves use system pressure to delay or sequence the components. So what we have going on here is, and they don't really show the innards of it, but usually it's some kind of like a spring-loaded check valve where once pressure gets to a certain level, it can override the spring. And so here you can see there's a free path for pressure to the door actuator to move it into the open position. And then you have a priority valve that you have to get a certain pressure before it'll send the gear pressure to the gear down. So what's going to happen is when you first move the selector valve, the free flow of fluid will go to the gear well. And you've seen this happen where when we actuate things on the 727, if you actuate more than the pumps can handle, or if you actuate it quickly, you get a drop in system pressure, right? So the pressure is a little bit lower when there's somewhere for the fluid to go. It's going to take the path of least resistance. But then once this door open actuator moves fully to its open position, that pressure is going to build back up in the manifold or in the supply line, And it's gonna, then the priority valve will open and send pressure down to that gear well or that gear, the gear actuator itself. Okay, and it'll put the gear down in this case. When it goes up, it does the same kind of a thing. So now if we port fluid over here, if we were to flip this valve, to the up position, and fluid will be ported over to the right, you can see it'll freely flow to the gear side. Once the gear's up, then it'll overcome this door well priority valve, and that will send fluid to push the door actuator to the left. Okay. So the way to remember these, that I do, is priority and pressure start with the same letter, right? Sequence valves are mechanically actuated, nothing easy there to remember. But it's not a priority valve which uses pressure. Priority valves use pressure, P and P. Okay, sequence valves are mechanical. They do the same job. You can serve the same basic function, they just operate in slightly different ways. Okay. In some cases, we want to make sure that our fluid flow is even no matter where it goes. So fluid will take the path of least resistance, right? And sometimes maybe one gear is a little bit easier to push down than the other. Or one door is a little bit heavier than another and it's going to be harder to operate. If you have a bigger cargo door versus something else. So if you have items or flight controls, you'll have more, for whatever reason, there'll be more load on one than the other. If you have like a crosswind, you'll have more load on one flight control than the other. So you don't want all the fluid to go to the easy to move side. So a flow equalizer valve essentially looks at the downstream pressure, and if one side's higher than the other, it closes off, it restricts the flow of fluid to the side where it's got a high flow rate, and it more freely allows the fluid to go to the side with the more restricted flow, or the lower flow rate, in order to equalize the pressure on both sides. So flow equalizing valve is going to split that flow evenly. In this case, we want both gear to go down at the same time. If you didn't have this, for instance, and one of these gear down actuators was, say, a little bit more worn out than the other, typically a worn actuator actually moves easier than a new actuator because the seals have worn down, it's broken in, so to speak. So that gear would tend to move faster or quicker than the other one. So what would happen is you'd get one gear would, the easier to move gear would come up first, and then once that actuator stopped moving, then the pressure would go to the other side. But you want both gear to come up together, so you put in one of these flow equalizing valves so that even if one side's a little bit easier to move, you're going to get even retraction of both or all three gear. So, or flight controls or other, items like that. Okay. And it'll actually work in both directions. It can equalize the flow of fluid going back too. If we move this into the, into the up position, rotate our valve, right? The fluid flow equalizer valves can go both ways. They can split a stream of fluid, or they can bring a stream of fluid back together at an equal flow manner. The other thing too is you don't want fluid flow from one actuator pushing, instead of flowing back where it should go, going into the other side. One gear pushes a gear down, and you're doing something like this. You don't want that to happen either. So it can prevent those kind of situations from occurring. Okay. So flow equalization valves or flow equalizer valves. In areas where we have a high chance of the flow rate becoming too high, i.e. there's a good chance that we'll get a broken line or a large leak, we don't want to drain our hydraulic system through that area. So where is an area where broken lines or large leaks are probably more likely than other areas? What's that? Landing gear well? Thinking the landing gear well? Any moving parts? Most moving parts are pretty good about not. They've designed and engineered these. As long as you install your hoses right and everything, the chances of it are pretty low. They don't use these all over the place. There's really only a few specific spots. Any ideas where our highest chance of a leak occurs in a hydraulic system? A leak caused by outside influence, outside forces. What's that? Threads? Well, if you've installed it right, it shouldn't leak, and you should leak check it after. So, I think Norman area. Someone said landing gear, but then said well. Where else on the landing gear? Where specifically on a landing gear do we send hydraulic fluid that is really close to FOD on the ground? What? The brake lines. Okay, that's the biggest area you'll see these. Almost every aircraft out is going to have a hydraulic fuse in the lines that go down to the brakes, because what you have is lines running down the leg of the landing gear, but then you've got a landing gear, a shock strut that has to be able to move. So you have a hose going from the upper part of the leg down to the brakes themselves. And those hoses are usually right between the wheels. If you go look at the 727, there's some hoses that are right between the wheels. So if you pick up a piece of FOD and chuck it into that area, there's a very strong chance that you can damage those. Those hoses are out, they're exposed, and they're near stuff. Okay, so if one of those hoses gets damaged, we don't want to hit the brakes and drain our hydraulic system. Right, so a hydraulic fuse is used there, just like an electrical fuse, that if the current's too high, current is like electrical flow. So if the flow of fluid is too high, we want to break that flow of fluid, right? A fuse breaks the circuit. If the current's too high, this is going to do it. So what we have is a restriction, and when we get a restriction, we're going to get a change, a difference in pressure across it, right? In this case, we have our inlet here, and the normal path is fluid flows in the inlet, it goes up and down through these openings, and it goes out the outlet. And there's a spring, so you have about the same amount of pressure on both sides of this piston, but we've got a spring over here that's kind of holding it to the left, helping to hold it open. But if all of a sudden, on our outlet side, we get a ton of fluid flow, our pressure is going to be high on the inlet, which is also going to be high on the left side of this piston, and we're going to have almost zero pressure to the right. So you'll no longer have this fluid pressure to the right of the piston helping to hold it as well. At that point, the fluid on the left is going to force this piston to the right, and it's going to close off those ports to the outlet. And it will stay that way until you shut the hydraulic system off. And the pressure bleeds down to zero. Okay? So the rate's predetermined. They decide, okay, the normal flow rate when you apply the brakes, for instance, is this. So if it exceeds that by more than 10% or 20%, they figure out what that delta pressure is and what spring pressure they need to make that piston move properly. What do we have to do with brakes where this could be problematic? Bleeding. When we're bleeding brakes, we're running a bunch of extra fluid through, right? So every time you go to bleed the brakes, you don't want this thing to close off because you'll never be able to bleed the air out of them. So they typically have a manual override where you can prevent this piston from sliding over in order to do maintenance operations, to bleed the system. So when we would bleed brakes, you'd have to go up and move a little lever on the hydraulic fuses so that they would not engage during brake bleeding. Now the nice part about ours is you would set those, when you shut the system off and the pressure bled to zero, they would automatically reset. But if you don't have ones that automatically reset, you need to make sure you don't leave them in the override position, otherwise they won't do the job they're supposed to do. Okay, so ours did have, some of the planes I worked on had the ability to have an auto reset, but not every one of these will automatically reset. Some of them, you can't let go of it. It'll always reset when you let go of the lever. So then, depending on how far apart they are, you either need a really, you're reaching up in the wheel well, and down here, it's a two-person job. Actually, it turns into a three because you need someone in the cockpit pushing on the brakes. So if you don't have a lever where you can lock it in the override position, you have to have someone holding that lever, you have to have someone doing the actual brake bleeding, and you have to have someone up in the cockpit doing the, pumping on the brake pedals. So, those are hydraulic fuses. Pressure control and regulating valves are our next thing. So these are a Pressure control valve is set to open at a set pressure. Okay. And usually they're used to bypass something. So if the pressure gets too high, they bypass. They can be used to set a pressure in a system. So this is the pressure control valve that sets the difference in pressure between, say, the pressure side of the system and the return side. If the pressure gets too high, it opens and allows extra pressure to bleed off onto the return side. That's what's integral to our hydraulic pumps, for instance. But then it is going to reclose if that pressure drops. A regulator is kind of an opposite. It's going to set a maximum pressure, and then it's going to close when the maximum pressure is reached. Okay. So pressure control, normal, is going to open at a set pressure and allow a bypass. Regulators are going to close. Typically, if they close and bypass, it's kind of a combination. It's a pressure control and regulator. So they can look something like this. So here we have a pressure control valve. Sorry, here we have a regulator. But the pressure control valve is like a check valve. A regulator here. Here's our inlet with a check valve to the outlet. Okay. That's the overpressure valve. But then if this is the pilot to open a path back to the reservoir. So if our inlet and our outlet, if you're going to have a differential pressure across this check valve down here, right? If this outlet side gets too high, it's going to push up on this spring, push up on the valve, and it's going to allow excess fluid to flow past the seat of the ball and out up here, and that's going to cut off, it's going to reduce the fluid going to B, and it's going to stop the B side from pressure from increasing until it drops back down to a point where it can override this check valve at the bottom. And then allow fluid flow again. So that's a regulator that has a bypass setting on it. I don't have a pressure control valve, but essentially it's this check valve right here working by itself can operate as a pressure control valve. So that wraps up our various types of valves. Now we'll move into actuators. And based on timing, oops, wrong button. Based on timing, I'm going to give you a break and we'll come back.